We're solving problem 15 from the fall AMC 12A from 2021. Recall that the conjugate of the complex number w equals a plus bi, where a and b are real numbers and I is equal to the square root of -1, is the complex number. The conjugate of w is equal to a minus b1. For any complex number z, let f of z be 4i times the conjugate of z. The polynomial p of z is equal to all of that. Has 4 complex roots, z1, z2, z3, and z4. Let q of z be all of this here, and its polynomial whose roots are f of z1, f of z2, f of z3, f of z4. Where the coefficients of a, b, c, and d are complex numbers, we want to find the sum of b and d. So, well, first things first. Let's just try and solve for a sum of the numbers. By using Vieta's formulas, we get that the sum of all the roots is just equal to the sum. So that's z1, z2, plus z1, z3, plus dot dot dot, plus z3, z4. This is equal to the sum. Therefore, by this logic, we want to find b here. So b, in this case, is, well, this is the conjugate z here. So this is just equal to 4i squared, since you're squaring the z portion here. And then you multiply it by the conjugates of z1 times the conjugate of z2. And then this becomes really confusing really quick. And then our final thing is going to be the conjugate of z3 times the conjugate of z4. Okay. Now, due to conjugate properties, we can use one of them. We say that the conjugate of a times the conjugate of b is equal to the conjugate of a and b together. So therefore, our b can be reimagined as 4i squared times the conjugate of z1, z2, plus the conjugate of z1, z3, and you add up all the values until the conjugate of z3 and z4. Okay. Now, there's another property that we can use. As the conjugate of a plus the conjugate of b is equal to the conjugate of a plus b, we now know that b is simply equal to 4i squared times the conjugate of z1, z2, plus z1, z3, dot dot dot, and then plus z3, z4. And then you take the conjugate of all of that. Now, what this just does, this simplifies down to b is equal to -16, since I squared is -1, times 3, as all of this is, well, this is actually the conjugate of 3. And what this basically means is that this is still -48. The conjugate of 3, it's just 3 because there's no imaginary part to that 3. It's not an imaginary or complex number. So we can use the other Vieta's properties for the second one, d. So we can do that. So basically, what we can do is multiply all the roots together again by Vieta z1, z2, z3, z4 is 1. So that means that d is equal to, well, same principle earlier, 4i to the 4th power times, well, it's now just all these roots, z1 to z4, and the conjugate of all of them, z1, z2, z3, z4, take the conjugate. So d is equal to 256. Since there are two negative ones, those just cancel out to be 1. And this just ends up being 1. So this is times 1 is 256. We finally have our numbers. D is 256, B is negative 48. When you sum those up, B plus D is equal to 256 minus 148, or 208, and that is our answer for this problem.